We're going to be looking at Descartes' rule of signs and the conjugate root theorem, which tells us about the roots of polynomial equations. Looking at this polynomial and looking at the signs of each of the coefficients, we can see that we go from positive to negative, which is a sign change, negative to positive, which is a sign change, and then positive to positive, which is not a sign change. So this particular polynomial has two sign changes. Now we're going to be looking at what the sign changes mean in a polynomial in regards to the roots of the equation. Descartes' rule of signs says that anytime I'm given a polynomial p of x that has real coefficients and it's in standard form, if I count the sign changes of p of x, that will give me the maximum number of possible positive real roots. If I count the sign changes of p of negative x, which just means I plug in a negative x everywhere I see an x, that will give me the maximum number of possible negative real roots. Now remember, when you plug in a negative number and then you apply an exponent, the only time the sign will change is when the power on the exponent is odd. Now this will give us the maximum possible positive and maximum possible negative real roots, but this number can decrease by 2 to find more possible real roots. So I know this sounds a little confusing, but think about the last example. We had two sign changes, okay? So two sign changes for p of x, which means that I'm going to have two possible positive real roots, 2 or 0 because I decrease by 2 to find the other number. So I'm going to have 2 or 0 positive real roots for that particular p of x. Alright, so let's look at this polynomial and count the sign changes. So how many total roots should p of x have? Well, that's using the fundamental theorem of algebra, which says since this is in standard form and the highest degree is 5, I should have 5 roots. Now, counting the positive real roots, I have to look at the sign changes. So 4x to the 5th, that's positive. And then 3x to the 4th, that's positive. Negative 2x cubed, so that's negative, positive, negative, positive. So let's count the sign changes. That's no sign change. That's 1. That's 1. That's 1. That's 1. So I have 4 sign changes, which means I will have 4, 2, or 0 positive real roots. Alright, so remember you have your maximum amount and then you decrease by 2 until you get to 0. Now, how many negative real roots? Well, now I have to look at my polynomial, and everywhere I see an x, I think that I'm plugging in a negative x. Now, if I plug in a negative x here to an odd power, the sign's going to change. So the sign's going to go from positive to negative. If I plug it in here, it's even, so the sign will not change. Plug it in here, the sign will change because it's odd. Plug it in here, the sign will not change. Plug it in here, the sign will change. And then the constant obviously will not change because it has no x value. So counting the sign changes, I have 1, 0, 0, 0, 0. So I have 1 negative real root. For sure, okay? So for sure, I will have 1 negative real root. So let's fill in this chart to help us figure out what the roots of this equation are going to look like. So let's say I have 4 positive real roots. Well, I know for sure I'm going to have 1 negative real root, and I'm not going to be able to have any imaginary because I have to total 5 roots, because 4 plus 1 plus 0 gives me 5. Now let's say I have 2 real roots. Well, again, I know for sure I have 1 negative real root, so that leaves me with 3. So I'm missing 2 roots to total up to 5, so I must have 2 imaginary roots. Now let's say I have 0 real roots. I know I still have 1 negative real root, and that leaves me with 4 roots that are left over to total to 5, so I must have 4 imaginary roots. Let's think back to when we used to solve quadratic equations. When did we ever get imaginary or irrational roots? Now, the only time we were able to get imaginary or irrational roots is by square rooting or using the quadratic formula. Now, how many roots does the quadratic formula give us if the solution is imaginary or irrational? Remember, we always got 2 because of that plus or minus sign that goes out front of the radical. So anytime I have a complex or irrational root, they come in pairs. If I have one, that means there's another one. Now, the conjugate root theorem tells me that if I have a polynomial that has rational coefficients, so yes, that's important, then the irrational roots of that polynomial come in conjugate pairs. So let's remember what the word conjugate means. It means that they differ only by the sign between them. So if a minus the square root of b is a root, then a plus the square root of b is a root. Very similarly, if a polynomial with real coefficients has a complex root, then its conjugate pair is also a root. So if a minus bi is a root, then a plus bi is a root. So they come in pairs always. This is due to that plus minus sign outside of the radical for the quadratic formula. So let's say I have a polynomial and it has rational coefficients, and it has the following roots. So I know for sure that 1 plus I and the square root of 2 are roots of this polynomial. I want to figure out if I can find any other roots of the polynomial. Well, if 1 plus I is a root, then that means 1 minus I has to be a root. If the square root of 2 is a root, then that means the negative square root of 2 is a root because these are conjugates. So in addition to these, I also have 1 minus I, and I also have negative square root of 2 as roots. Now we want to write a polynomial function that's going to have rational coefficients so that p of x equals 0 is going to have the following roots. Now, if we have the root 1 minus the square root of 3, remember because of the conjugate theorem, that means we have 1 plus the square root of 3 as a root also. Now, how we go from the roots to writing the function, we need the linear factor that represents that root. Now, remember, that's always x minus a, where a is a root. So the linear factor that will represent 0 is going to be x minus 0, which is just x. The linear factor that represents 1 minus the square root of 3 is going to be x minus 1 minus the square root of 3, which, simplifying, just distributing here, we get x minus 1 plus the square root of 3. And then looking at our conjugate root here, 1 plus the square root of 3, it's going to be x minus 1 plus the square root of 3. And when we distribute, we get x minus 1 minus the square root of 3. So here are our 3 linear factors for our polynomial. Now, how we get our function, we have to multiply them out. So I'm going to set it up. We have p of x equals x times x minus 1 plus the square root of 3 times x minus 1 minus the square root of 3. Now, because these two are conjugate linear factors, that means that special things will happen when I multiply them together. Lots of stuff will cancel out. So I'm going to want to multiply these first. Once you have everything multiplied out, you need to combine like terms and simplify things that cancel out. The last step is to multiply everything by the x out front. So we'll get p of x equals x cubed minus 2x squared minus 2x. And this is going to be my final answer. This is my polynomial function that has the roots 0, 1 minus the square root of 3, and 1 plus the square root of 3. Now notice I have 3 roots and I have a cubic function, which is exactly what I should have based on the fundamental theorem of algebra. Go ahead and give these a try. Remember, anytime you're using a square root in your answer, instead of using the symbol, you're welcome to just say square root and then put your number in parentheses.